Namaskar and I welcome all of you to my YouTube channel. This is lecture number 2 on magnetic properties of solids. First, let me write down the topics that I'll be covering today. In first topic, I will define magnetism. Here, I will explain the root cause of magnetism. Next, different types of magnetism in solids. Types of magnetism. Next, different types of magnetic materials. In last topic, I will explain different types of magnetic moments of an electron. Different types of magnetic dipole moment of an electron. Here we will learn orbital magnetic dipole moment as well as spin magnetic dipole moment of an electron. Now let me explain the first topic, which is magnetism. Students, in my previous lecture, I already mentioned you that every atom in a material behaves like a magnetic dipole. This presence of tiny magnetic dipoles in a material is known as the magnetism. In other words, we can say that the root cause of magnetism is presence of tiny magnetic dipoles in a material. First, let me write these points. The presence of tiny magnetic dipoles in a material is known as magnetism. Okay? That means the root cause of magnetism is presence of tiny magnetic dipoles. Next, one important point is that all materials show up magnetism. Why? Because all the materials are consisting of atoms. For example, iron, nickel, cobalt, even plastic will show magnetism property. Okay? Next, types of magnetism. Students, magnetism in solids has been classified into 5 categories. Number 1, diamagnetism. Second one, paramagnetism. Third one, ferromagnetism. Fourth one, antiferromagnetism. And fifth one, ferrimagnetism. First, let me write these points. Magnetism in solids has been classified into 5 categories. Number 1, diamagnetism. Number 2, paramagnetism. Number 3, ferromagnetism. Number 4, anti-ferromagnetism. Number 5, ferrimagnetism. Students, in this lecture series, I will give detailed explanation on these 3 topics only. Okay? In the remaining 3 topics, I will give brief introduction only. Okay? Next, types of magnetic materials. There are 5 types of magnetic materials. Types of magnetic materials. First one is diamagnetic materials. Second one is paramagnetic materials. Third one is ferromagnetic materials. Fourth one is antiferromagnetic materials. And fifth one is ferrimagnetic materials. Here also I will give detailed explanation on these 3 topics only. So in next section I will give some properties of diamagnetic, paramagnetic and ferromagnetic materials. Okay? Next, some important properties of diamagnetic, paramagnetic and ferromagnetic materials. For diamagnetic materials, relative permeability is less than 1 and magnetic susceptibility is negative or less than 0. One important point is that for diamagnetic materials, the magnetic susceptibility is independent of temperature. Okay? Next, for paramagnetic materials, relative permeability is greater than 1 and magnetic susceptibility is positive and greater than 1. Here magnetic susceptibility depends on temperature. Okay? Again, for ferromagnetic materials, relative permeability is very greater than 1 and magnetic susceptibility is positive and very greater than 1. Here also magnetic susceptibility depends on temperature. I will give detailed explanation on these topics in my upcoming lectures. Okay? Next, different types of motion of an electron in an atom. Students, an electron in an atom has 2 types of motion. First one is orbital motion around the nucleus and second one is spin motion about its own axis. Due to orbital motion, this electron has orbital magnetic dipole moment, and due to spin motion, this electron has spin magnetic dipole moment. Now let me write these points. An electron in an atom has 2 types of motion. Number 1, orbital motion around the nucleus, and number 2, spin motion about its own axis. In my next section, I will derive the mathematical expression for orbital magnetic dipole moment of an electron. Okay? Next, I am going to derive a mathematical expression for orbital magnetic dipole moment of an electron. Students, for this case, I am considering a simplest type of atom in which an electron is revolving around the nucleus in a circular orbit of radius r in anti-clockwise direction. We assume that the mass of this electron is m and instantaneous velocity of this electron is v. Since the electron is revolving around the nucleus in anti-clockwise direction, so therefore the direction of orbital angular momentum will be coming out of this board and it is denoted by this arrow. Okay? So this is the direction of orbital angular momentum of this electron. Again, since the electron is revolving in anti-clockwise direction, so therefore the direction of current will be in clockwise direction, because the direction of electron flow and direction of current flow are always opposite to each other, and because of this current flow, the direction of magnetic dipole moment will be going inside this board and it is denoted by this arrow. So this is the direction of orbital angular momentum of this electron. Okay? And we are going to find out the mathematical expression for this value. Okay? Now let me write these points. Let us consider an electron of mass m is revolving around the nucleus in a circular orbit of radius r with angular velocity omega. Okay? The magnitude of current, due to rotation of electron will be I is equal to charge of the electron divided by time period of this electron, which is equal to E divided by twice pi r divided by V. Now let us understand how time period of this electron is equal to twice pi r divided by V. Students, from physics we know that velocity is equal to distance divided by time, or time is equal to distance divided by velocity. Now the total distance covered by this electron to complete one cycle is twice pi r, which is the perimeter of this circle, and velocity of this electron is v. So therefore time period of this electron will be twice pi r divided by v. After simplifying, we will get current I is equal to E into V divided by twice pi r. Okay? Because of this current, this circular orbit behave like a current carrying loop. In other words, we can say that it is equivalent to a magnetic dipole, and the magnitude of magnetic dipole moment can be obtained by multiplying current and area of this loop. Now let me write these points. the magnitude of orbital magnetic dipole moment of the electron will be current into area of the loop. For this case, current is equal to EV divided by twice pi r, and the area of this loop will be pi r square. So, after simplifying, we will get E by 2 into V r. After rearranging, we will get E divided by twice m into mvr. We know that mvr is equal to the value of orbital angular momentum. Okay? So, this can be written as E by twice m into magnitude of orbital angular momentum of this electron. Okay? Suppose this is equation number 1. In vector form, equation 1 can be written as equation 1 can be written as mu L vector is equal to minus E by twice m into L vector. Here negative sign indicates that both L vector and mu L vector are opposite to each other. So, here negative sign indicates that both L vector and mu L vector are opposite to each other. Suppose this is equation number 2. More precisely, equation 2 can be written as equation 2 can be written as mu L vector is equal to minus ZL into E by twice m into L vector, and this is the mathematical expression for orbital angular momentum of the electron. Here ZL is known as the Landy Z factor for orbital motion. Okay? Always remember this expression. Finally, please note down some important points. Number 1. Gyromagnetic ratio. From equation 1, we have mu L vector is equal to E divided by twice m into L vector. After rearranging, we will get mu L vector magnitude divided by L vector magnitude is equal to E divided by twice m, and this ratio is known as the gyromagnetic ratio. Now let me write the definition. The ratio of magnitude of orbital magnetic dipole moment to orbital angular momentum of an electron is a constant quantity, and this ratio is known as gyromagnetic ratio. ठीक है. The value of gyromagnetic ratio will be E divided by twice m, which is equal to charge of an electron 1.6 into 10 to the power minus 19 coulomb, 2 into mass of the electron 9.1 into 10 to the power minus 31 kg. After simplifying, we will get 9.8 into 10 to the power 10 coulomb per kg. ठीक है. Next, note number 2. Here I will define the term what is Bohr magnetron. From quantum mechanics we know that the magnitude of orbital angular momentum is equal to small l into small l plus 1 into h cross, where small l is known as the orbital or azimuthal quantum number, and h cross is known as the reduced Planck constant, which is equal to Planck constant divided by twice pi. So, if we substitute this value in this equation, we will get equation 1 implies mu L vector is equal to E divided by twice m root over small l into small l plus 1 into h cross. After rearranging, we will get E h cross divided by twice m into root over L into L plus 1. This quantity E h cross divided by twice m is known as the Bohr magnetron. So, finally we get mu L vector magnitude is equal to mu b into root over L into L plus 1. Here mu b is equal to E h cross by twice m is known as the Bohr magnetron, and it is used as a unit of atomic dipole moment, and the value of Bohr magneton will be the value or magnitude of Bohr magnetron will be or equal to E h cross divided by twice m, we know that h cross equal to h divided by twice pi. E h divided by 4 pi m. Now let us substitute the values. Charge of the electron 1.6 into 10 to the power minus 19 coulomb. Planck constant 6.626 into 10 to the power minus 34 joule second, divided by 4 into 3.14 into mass of the electron 9.1 into 10 to the power minus 31 kg. So after simplifying, we will get mu b is equal to 9.27 into 10 to the power minus 24 ampere meter square. Okay? Always remember this value. Now let us recap what we have learned till now. Students, we derive the mathematical expression for orbital magnetic dipole moment of an electron whose value is minus GL into E divided by twice m into L factor, where GL is known as the Landy Z factor for orbital motion and its value is 1, and magnitude of orbital angular momentum according to quantum mechanics is root over small l into small l plus 1 into h cross, where small l is known as the orbital or azimuthal quantum number and h cross is known as the reduced Planck constant whose value is h divided by 2 pi. Similarly, we can show that spin magnetic dipole moment of an electron is given by minus Gs into E divided by twice m into s vector, where Gs is known as the Landy Z factor for spin motion. It should be noted that for free electrons, the value of Gs is almost equal to 2. Okay? And the magnitude of s factor is equal to root over small s into small s plus 1 into h cross, where small s is known as the spin quantum number and as usual h cross is the reduced Planck constant. The vector sum of orbital magnetic dipole moment and spin magnetic dipole moment will give the total magnetic dipole moment of the electron. Okay? So this is all about today's video and I hope that you have learned a lot from this video.